Welcome to Lesson 7.1. Today we're going to talk graphing exponential functions. There are 6 vocab terms for this section. Go ahead and pause the video and get these written down, and then I'll go through them. The first one is an exponential function. That is a function in the form of y is equal to a to the x, where the independent variable is the exponent. We have exponential growth, and that's the function in the form of y is equal to a to the x, where our base is greater than 1. An asymptote is a line that a graph gets very, very close to, but never crosses. It could be a vertical asymptote, a horizontal asymptote, or a diagonal asymptote. A growth factor is the base of the exponent in an exponential growth function. So if we know it's a growth function, that base is going to be our growth factor. We also have an exponential decay, and that's a function in the form of y is equal to a to the x, where a is between 0 and 1. And then the decay factor would be the base of the exponent in an exponential decay function. So if we know it's a decay function, that base is our decay factor. So an exponential growth function is pictured on the right here. You'll see that from left to right it gets increasingly larger. The parent function is f of x is b to the x, where b is greater than 1. The types of graphs, it's a continuous graph, it's 1 to 1, and it's increasing. The domain of an exponential growth function is all real numbers. The range of the parent function is all positive real numbers. That'll change based off of any vertical shifts that we have. The asymptote starts out as the y-axis, and again, that will change too if there's any vertical shifts. And then the intercept is 0, 1, which again can change if we move the graph up or down. We also have the exponential decay function. If you look at the graph, it's pretty much the opposite of the growth. It starts out very, very high, and then it gets very, very small very quickly, and then it levels out. The parent function is the same as the growth, b to the x, but now our base is between 0 and 1. The type of graph, it's still continuous, it's still 1 to 1, and it is decreasing. Domain is still all real numbers. The range is still all the positive real numbers, but again, that can change with vertical shift. The asymptote is the y-axis, but again, that can change, and the intercept starts out as 0, 1, and again, that can change as well. So graphing an exponential function, you can make a table of values, you fill out the table, you plot the points, and you connect them, or you can graph them on your calculator and sketch a graph from that, but we'll do the table for a couple of examples. So if we have the equation y is equal to 3 to the x, that is an exponential function because our variable x is in the exponent. If we want to graph that, we make a table of values. The standard table goes from -2 to 2. And if I plug each one of these values in, 3 to the -2 power gives me 1/9, okay, which is 0.111 repeating. Either way, it doesn't really matter. -1, 3 to the -1 power is the same as 1/3, which is 0.33 repeating. 3 to the 0 is the same as anything to the 0 power. That's going to give us 1. 3 to the first power is just 3. And then 3 squared gives us 9. So if I go to plot these points with the decimals, I'm just going to do the best that I can. When x is -2, y is 0.1 repeating, so I want to put the dot as close to the axis as I can, so right about there. For -1, it's at 0.33, so it's just a little bit higher. So it's somewhere in that area. We've got 0, 1, we've got 1, 3, and we've got 2, 9. So those are my points. I connect them with as best a graph as I can, and this should be roughly what my graph looks like. Our other example, we've got 1/3 to the x. So when I do this, again, I do the same thing. So now I'm going to take 1/3 to the -2 power, and that's actually going to get us a 9 for a value. For -1, I'm going to do 1/3 to the -1. That's going to get me 3. To the 0 power, again, anything to the 0 power is just 1. 1/3 to the first power is just 1/3, which again is 0.33 repeating. And then 1/3 squared is the same as 1/9, which again is 0.11 repeating. So again, I can plot these points, -2, 9, -1.301, 1.33, and then 2.11. And again, connect these with our graph. And that's what the graph of 1/3 x roughly looks like. This won't be on the check-in, but it's always good to know how to graph these. But like I said before, you can do this on the calculator, so we're not going to spend a whole lot of time on it. These are all of the transformations we can do to the exponential functions. They're the same as when we did it for regular functions, but they'll look a little different. So go ahead and pause the video, get all these written down before I go through these and explain. If we add onto our equation at the end, so outside of our exponent, that's going to move the graph up, and it's going to move it up whatever we add to it. The same thing if we subtract at the end, that's going to move the graph down however far that we are subtracting. If we subtract in the exponent to our variable, that's going to move it to the right. If we add in the exponent to our variable, it's going to move it to the left. If we make the whole equation negative, it's going to reflect our graph across the x-axis. If we just make the variable in the exponent negative, that's going to reflect the graph across the y-axis. If we multiply the whole exponent, so the base and the exponent, by a value k, that's going to vertically change our graph. It'll vertically stretch the graph if we multiply it by something greater than 1. It will vertically shrink the graph if we multiply it by something between 0 and 1. And finally, if we multiply our variable in the exponent, that's going to horizontally change our graph. It'll horizontally stretch it if we multiply it by something between 0 and 1, and horizontally shrink it if we multiply it by something greater than 1. So just like before, vertical and horizontal stretches and shrinks are opposite of each other. Vertically stretch is greater than 1, horizontal shrink is greater than 1. Vertically shrink is between 0 and 1, horizontally stretch is between 0 and 1. So make sure we have these written down somewhere. We will be using these for the rest of the lesson. So what we're going to do is we are going to describe the transformation. So we're going to determine whether it's a growth or decay function based on our base. We're going to find a horizontal shift, vertical shift, whether it's a stretch or compress, and how it is, vertical, horizontal, whatever, and then the reflection as well. Okay, so our given equation is y is equal to 2 raised to the x plus 3 minus 5. So first of all, whether it's growth or decay, we look at our base. Okay, again, if the base is greater than 1, which it is, it's going to be a growth function. And this is a exponential growth because 2 is greater than 1. For our next one, our horizontal shift, we look at the exponent. Okay, you see that we're adding 3 to it. Adding means we go to the left, and then how far is the number that we're adding. So the horizontal shift is left 3. For our vertical shift, we look outside of our exponent, we're subtracting 5. Subtract means we move down, and then 5 is how far we're moving down. For our stretch or compress, we look at, are we multiplying the base by anything? So yes, there's a 2 here, but we're looking to see if we're multiplying the 2 by anything, and we're not. Okay, so when that is the case, there is no stretch or compress. Okay, you also notice that we're not multiplying x by anything either. Okay, so when neither one of those are being multiplied, we're not doing any stretch or compress. And finally, for the reflection, we look, do we have a negative out in front or a negative for our variable? They're both positive. And it's kind of hard to see with the circles, but if you look, the 2 is positive, the x is positive, so that means there is no reflection as well. Okay, so this is what we're going to be expected to do in our check-in. We're going to do the same thing for our next example. Now our equation is y is equal to 0.1 times 6 to the x minus 3. So again, whether you're looking for growth or decay, we look for just the base of our exponent. The base is 6. 6 is greater than 1, so this is a growth function. Okay, for our horizontal shift, we look in our exponent. Okay, it's just x. We're not adding or subtracting anything, so we do not have a horizontal shift. There is none. For our vertical shift, we look outside, we're subtracting 3. Again, subtracting means down, and then we're going to move down 3. For a stretch or compress, we look at, are we multiplying the base by anything? Are we multiplying the variable by anything? Okay, the variable doesn't have a number in front of it, so there's no horizontal stretch or compress, but we are multiplying the base by a 0.1. Okay, 0.1 is between 0 and 1. That means it's a vertical shrink. Okay, and it's by a factor of 0.1. So we would write vertical shrink 0.1. And finally, for our reflection, we look, is our base negative, is our variable negative? They're both positive, so we will not have a reflection. Doing the same thing for our next example, we've got the equation y is equal to 2 times 1/4 raised to the x plus 2 minus 3. First question, is it growth or decay? Again, you look at just the base. The base is 1/4, that's between 0 and 1. That makes this a decay function. For our horizontal shift, we look at how we are changing our x. We are adding 2 to the x. When we add, that means we move left, so we're going to go to the left 2. Our vertical shift, we've got a minus 3 on here. Minus means down, so we're going to move down 3. Okay, any stretch or compress, again, you look at, are we multiplying x by anything? No, so there's no horizontal stretch or compress. There is a 2 out in front. Okay, a 2 is greater than 1, so that means this is going to be a vertical stretch by a factor of 2. So we would say a vertical stretch of 2. For the reflection, again, is the x negative? Is the base negative? Neither one are negative, so we will have no reflection. Our next example, we've got y is equal to negative 3 times 2/5 raised to the x minus 4 plus 2. So again, growth or decay, we look inside the parentheses at our base. It's a 2/5. 2/5 is between 0 and 1. That makes this a decay function. For our horizontal shift, we're subtracting 4 from our x. Subtract means we move to the right, so we're going to go to the right 4. Our vertical shift, if we look outside the exponent, we're adding 2. Adding means we move up, so we're going to go up 2. Stretch or compress, for horizontal, again, we look at, is x being multiplied by anything? And it's not, so there's no horizontal stretch or compress. Vertically, we look in front, there's a 3 there. Don't mind the negative right now. 3 is greater than 1, so this is going to be a vertical stretch by a factor of 3. Okay, so we take just the positive version because the negative is going to help us with our reflection. So the reflection, x is positive, so there's no reflection about the y-axis. However, there is a negative out in front, so we are going to reflect it across the x-axis. Okay, so that's what the negative does. We don't worry about that with the stretch or compress. We only take the positive number there. The negative only goes with the reflection. Go ahead and pause the video. Do this last example on your own with y is equal to 3/8 times 5/6 raised to the x minus 1 plus 1, and then hit play and see how you did. You should have found that this is a decay function that shifts to the right 1, up 1, a vertical shrink by a factor of 3/8 with no reflection.